Hello, everybody. Welcome to the Flang update. I'm Steve Scalpone, the manager of the high performance compiler team at NVIDIA, and I'll be joined today by three other leaders of the Flang community to talk about the current state of Flang. Flang was started as a collaboration in 2017 between the NNSA labs and NVIDIA, where we open sourced a Fortran compiler in May of 2017. That compiler is still under active development under Flang compilers. Since then, we decided to start again from scratch, and we did. And Flang was accepted as an LLVM subproject a couple of years ago. It's been in the mono repo since 2020. Now it has over 200,000 lines of code, including tests, up from 160K last year. We have build bots, web pages, documentation all online, a couple of regular calls, technical and administrative, and some specialties from some of the subgroups. One of the things that's been built is a Flang driver. Every compiler needs a driver, and it's the command line interface that is used to pass commands down to the compiler. Now it's modeled on the Flang driver, and the code is shared directly from the Flang driver subdirectories. The long-term plan is to extract that code from Clang into its own subdirectory and put that in the front end. The CLI attempts to be compatible with Clang and G-Fortran, where there's Fortran-specific options. As you can see right here for some command line option example of G-Fortran and Flang new, which is the name of the driver, where there's an option given to show the size of an integer, the default integer. And here we're setting it to 8. That's Fortran specific. The Flang front end is mostly complete. It has an integrated scanner, a parser, a preprocessor, does all the semantics, does everything from standard Fortran 77 to Fortran 2018. And there's even some talk about putting in some future proposed features that are in Fortran 2023. Most of the common extensions and deprecations are documented and implemented in their tests as well. From the front end parser, we lower down to a FIR or MLIR, and then to LLVM IR. Now that's all been developed in a separate repo called Flang Compilers LLVM project, and it's being upstreamed right now, piece by piece. It's actively being reviewed, and those changes are being merged upstream. I also want to point out that there's an introduction to the Flang front-end tutorial that's scheduled for Friday at noon Pacific time. So please attend that. And I'll turn it over to Eric Schweitz, who will talk about FIR.
Thanks, Steve. So FIR is a dialect of MLIR used in the high-level representation of in Flang. It was first presented in the developers meeting in San Jose in 2019. Here I'm going to summarize the recent advancements that we have been making as we work on lowering Fortran programs to FIR. One of these is using the MLIR built-in types and ops for floating point, and removing the FIR ops. We have better support for character types and optional arguments. Those are Fortran. We also support Fortran functions that have caller allocatable semantics. So that's similar to like an S return in LLVM. Some more improvements have been made to hide details of manipulating box values, extending slices, the slice operation to work intra-object. We allow easier integration with the runtime, so we've made some changes there. Finally, array operations have been added to allow abstraction of Fortran's copy in and copy out semantics. There's an example here in this fragment of code. At first, the arrays on the left and right-hand side are copied using the array load operations. Then you'll notice there's a loop structure that builds the values element by element. And inside that loop, there's a fetch operation that's fetching a value from one array, and then it adds 1 to that and updates the second array. You can also see that the array value being updated is threaded around the loop as an SSA value. And lastly, the copy that's being recorded by the updates is copied out to the destination array in the merge store. With that, I'll hand it over to Kiran.
Hi, I will provide the OpenMP update for Flang. So what we have on this slide on the right-hand side shows the high-level flow of the OpenMP handling in Flang. So we have the traditional compiler flow, including parsing and semantic checks. After that, the parse tree is lowered to the high-level IR based on MLIR, which Eric talked about. The Fortran portion is represented by FIR, and the OpenMP portion is represented by the OpenMP MLIR dialect. For lowering to LLVM, we deviate from the traditional MLIR flow. MLIR dialects usually convert to the LLVM dialect, but the OpenMP dialect does not. It exists along with the LLVM dialect, and the OpenMP MLIR operations are converted to LLVM IR using the OpenMP IR Builder. The OpenMP IR Builder project basically contains functions for generating LLVM IR and runtime calls for the OpenMP constructs and clauses. It contains mostly code refactored out from the Flang project. In this slide, we have an example. So one of the constructs that we managed to implement end-to-end is the OpenMP work sharing loop. The first table that we see on this slide shows an example. On the left-hand side is the Fortran source code. Here we have a work sharing loop which iterates over from 1 to 100 and fills an array ARR with the value of I. On the right-hand side, we can see the MLIR portion. Basically, we see the OpenMP dialect operation omp.ws loop. In the body of the loop, we see code which computes the location of the ith position in the array and storing the value of I to it. So the first major milestone that we have for OpenMP support is version 1.1, and we are targeting to complete this by the end of the first quarter of next year. So OpenMP 1.1 has all the major constructs and clauses like parallel, work sharing loop, reduction, etc. And these constructs and clauses are widely and commonly used in various applications. The second table shows the status of the implementation of these constructs and clauses. We have 3 columns. The first column is the completed constructs. We have completed parallel, the work sharing loop, master, critical, barrier, and flush. We have the sections, atomic, ordered, thread private, and various data sharing clauses in progress. Work on single, reduction, and copy-in is not started. So that was a quick update about the OpenMP support in Flang. Now I hand over to Valentin for giving the OpenACC support and also saying the final words.
Let me give you a brief status update about OpenACC support in Flang. We are building OpenACC support in Flang and LLVM with a top-down approach from the parser down to the runtime. The code is currently targeting version 3.1 of the OpenACC standard specification. As Flang is based on the FIR dialect, we have also an OpenACC MLR dialect, same as the OpenMP support. You have here a list of everything that is available upstream, and future work will focus on the MLIR to LLVM translation and extension of the runtime. So you can find all the source code in GitHub, and we are inviting you to join the Flang roundtable this week and check out the project anytime. Thank you.